Okay, so we're on question 2, and it's all about springs and Hooke's law by the looks of things. Think springs and Hooke's law aren't interesting or useful? Check out this guy who basically lived off rabbits as a kid because they were so poor.
Deadly accurate with a bean shooter since he was 10 years old. But it was no childhood game then. It was a matter of survival. His eyesight is also good enough to use these rocks to pick off a quarter in midair.
There it goes.
Yeah, you hit it.
Is the evidence there?
The evidence is here. You got it.
That's souvenir.
The evidence is a chip just left of the L in Liberty.
Anyway, hope you found that interesting. So let's have a quick read of the question. So we are told a Newton meter measures the weight of objects. Look at figure 3. Here is figure 3. What is the weight of the object in figure 3? So you can see this little hook here. This is the weight, and you've added the weight and it's got a reading. So you simply have to read accurately off this scale. So I'm going to zoom right in, but obviously you have to get your eyes in close and read here what that value is, right? So it's in between 5 and 6. It's dead in the center, so it's obviously 5.5. Right, they've already given me the unit there, but if it wasn't there, I'd have to write in newtons as well. Okay, so elastic materials return to their original shape, right? That's what they do. So the spring inside the Newton meter behaves elastically. What happens to the length of the spring when the object is removed from the Newton meter? So I've hung the weight, I take it off, it goes back to its original shape, so the spring gets shorter. Right. A student will investigate a practical to investigate the extension of the spring. Write a method the student could have used. 4 marks. Don't just skip it because it's a 4-mark question. I've got a video on this if you want to see. So if you go to my channel, you'll find a required practicals playlist, and here is the required practical for force and extension.
Okay, so this is the AQA required practical for Hooke's law.
I think I show in this one, I'm using I'm getting a value of 8.4. So I'm using a pointer here to measure, and I've waited till the spring is stationary. Right, so there's a couple of things we need to mention, right? So if I draw a quick picture, right, you set up a clamp stand, right, with a boss which holds your meter ruler. You could set up and make sure your meter ruler is straight as well. Like you see, I've drawn this and it's kind of wonky. You need to make sure your meter ruler is straight. Secondly, you can get a second clamp stand, and off this one you can hang your spring. Right? Now you can put a piece of paper or a bit of a splint or something on the bottom of the spring to mark on the meter ruler where you are, right? And then you've got the hook onto which you add your weights. So what are we going to do? So my handwriting and my spelling is terrible. I'll write it as neatly as I can. Step 1. You can try and make 4 points.
You can do 4 bullet points if that would help, to try and hit all the marking points. So step 1, set up 2 clamp stands on bosses to hold the meter ruler and spring. Okay, 2, attach marker to the spring to assist with making length readings. Right, 3, take first length reading, right, without any weight. Without any weight. 4, try and do it with correct grammar, capital letters. Add weight, record new length. Right, so add a weight, record a new length. 5, subtract original length from new for extension. What am I on about? Right? When you get a spring and you hang a weight from it, it gets a bit longer, right? But if your spring started out 10 centimetres long and it got longer to 12 centimetres, the extension is not 12 centimetres, the extension is just 2 centimetres. And the examiners are very keen on making sure that you make that clear. So you have to always mention that you are getting the extension by taking the original length and the new length and subtracting them from each other. That's why that's all been mentioned. That's because I'm trying to hit those marking points. Okay, so have I said enough? Oh yes, and then finally, like really go the extra mile here. Repeat for the same weight. So you can take an average, and others. So
you can imagine you would have a table, and it would be weight, and you could have length, and then you could have extension, right? And if you was to record these three values, weight in newtons, length in meters or centimeters, meters as well, if you was to record these three values, or record the weight values and the length values, you could then go ahead and calculate your extension values, and that's what you'd do to do this experiment. Right, a lot of writing there, a lot of writing, but 4 whole marks, definitely worth it. Right, let's go on to the next bit. What could be done to improve the accuracy of this experiment? Accuracy. Right. So, let's just go through them one by one. Use a pointer from the spring to measure the length. This sounds like a good candidate. I'm going to keep that one alive. Use a stronger spring in the practical. Well, actually I'm trying to find out about the spring, so changing the spring is not what I want to do. Use a new spring for each reading. Again, a new spring might be slightly different. That's not helping me at all. So I don't think so. Make sure the spring is stationary before measuring the length. That makes sense. Use a longer ruler when measuring the length. Having a longer ruler is not going to make my measurements more accurate, right? What makes my measurements accurate is the number of divisions on the ruler, so I can get down to a higher precision. So again, the length of the ruler is a no. Right, so this is exam technique. Whenever you go through a question where you have to pick, and it says tick 2 boxes, right? Tick 2 boxes. If you only tick 1 box, you're crackers, right? You've got to tick 2 boxes and just guess if you're not sure. But it makes sense to read all of them and to remove or put crosses next to ones you think sound dodgy. And then if you're stuck, you can always guess. But if you think you know the right answer, and I think I do in this case, I think that using a pointer, that makes sense. I suggested that in my video. And make sure the thing is not swinging around, make sure it's stationary. I think that also makes sense. But by pointing out to myself that I think that's silly, that one's silly, that one's silly, and then I have to guess from what's left, if I wasn't sure, I'd improve my chances. So that's good exam technique. Right, so the student added weights to the spring and measured the extension of the spring, and as we can see, as they added weights, as they added 0.5, we got a 2 centimeter extension. 1 Newton gave us a 4 centimeter extension, etc. Right. What is the relationship between the force applied and extension? Right, well, as the one goes up, so does the other. So what do we call this in mathematics? We call it proportional. And it's direct proportional because it's going straight from the center as well. It's going from the origin of the graph. So extension is inversely proportional to force. That would look like this. So that's not correct. Extension increases by smaller values for force as force increases. What would that look like? Well, that would look like force here, extension here, and the extension would increase by smaller values as force increases. So that would look like this, right? You'd need more and more force to get the same extension. Extension is directly proportional to force. That's the one, right? Direct proportionality. Very important word. A pairing of words worth learning. Use figure 4 to determine the additional force needed to increase the extension in the spring from 5 centimeters to 7. The additional force needed. Right, so let's have a look at figure 4. So if I was at 5 centimeters, the force I would need to be pulling this spring with would be 1.25 newtons in between 1 and 1.5. And to extend it to 7 centimeters would take a force of 1.75. So in order to go from 1.25 to 1.75, I can just subtract 1.25 from 1.75, which leaves me 0.5 newtons extra force needed, right? So 0.5 newtons, and they've given me the unit, so I don't need to write it here, but I just do because it's my habit. Okay, so table 1 shows some results from a different spring. Okay, a different spring. So at 0 force, 0 extension, as we would expect. So this would look like on a graph, it would look just like the one we've just seen. It would look like force, extension, and it would be a straight line going from the origin, sorry. Right? What would the extension be for a force of 2 newtons? So I need to look at this pattern here. Let's have a look. So going from here to here took a force, sorry, going from here to here was a force of 0.5, gave us an extension of 0.025 meters. Another 0.5 force added gave us another 0.25 newtons added. So the pattern looks pretty straightforward. To get to 2, which would be another jump of 1.5, should be the same jump in extension if it obeys Hooke's law, which it looks like it does. So that would get us up to, what is 0.075 plus 0.025. Well, if you're not sure, you can do it on your calculator, but it definitely comes out as 0.1 meters. Right, I think this is the final question. Cool, that was a long one. The spring constant for the spring in table 1 is 20 newtons for every meter. 20 newtons for every meter, that's what the slash means. Calculate the work done in stretching the spring until the extension of the spring is 0.05 meters. Use the correct equation from the physics equation sheet. So as soon as it says this, you turn to the front, or you turn to your equation sheet. So this is the equation sheet you would have. You have a check through, and what we're looking at here, right? Force, velocity, initial velocity, sorry, final velocity, initial velocity, no, that doesn't look right. Elastic potential energy, spring constant, extension, square, that looks correct, right? So if I can just take this formula, and this is what you must do, is write it in here. Just do that first. It's definitely worth doing that. Get it correct, K E squared, right. So, now, advice for doing this. Stick all your numbers in first, calculate what you can calculate, and you're less likely to make mistakes. So what numbers have I got? Do I have the elastic energy? No. But that's what I'm trying to find. It's the work done. It's the same as the work done. Do I have the number 1/2? Yes. Do I have the spring constant K? Yes, they've given it me, times 20, times by the extension, which is here, which is 0.05. Don't forget to square it. Right, this is where you break out your calculator. Hopefully you have your own one. So it's going to be 0.5, which is for the half, times 20 times 0.05 squared. And I'm getting an answer of 0.025 joules. 0.025 joules. Try and keep your answer nice and neat, otherwise the examiner might not be able to read it. They've given us the unit there already, so I didn't need to write it in. Okay, hopefully you found this one useful as well. Thanks for watching.